Have you ever wondered what the future of computing might hold? Imagine a computer that can solve problems in seconds that would take classical computers years to solve. That's the promise of quantum computing. Join us on a journey as we explore the possibilities of quantum computing, from its mind-bending physics to its incredible potential to transform the way we solve some of the world's most complex problems. From cryptography to drug discovery, quantum computing has the potential to change the world as we know it. So grab a cup of coffee and join us for this exciting adventure into the quantum realm. Don't forget to hit the subscribe button and turn on notifications so you don't miss any of our upcoming videos. Why quantum computing? Many areas require us to perform spectacularly complex computations, whether to advance our understanding or ensure our security. Some of these computational challenges exceed the capabilities of traditional computers, including supercomputers, because they cannot be solved or cannot be solved quickly enough to be useful. Optimization of complex systems, artificial intelligence, materials, and chemical simulation are examples of this, all of which require manipulating extremely large numbers. In chemical modeling, for example, every electron-electron interaction must be considered because every electron exerts an electrical force on every other electron. Just one more variable, an extra electron, increases the computing challenge exponentially. Understanding the exponential challenge. Consider the best seating arrangement for a table of 6 people. Traditionally, each of the 720 seating options is examined in turn until the correct answer is found. If we double the number of diners, we get 479,001,600 different seating options. This example demonstrates how a seemingly minor change in a problem leads to an exponential increase in the number of potential answers, and thus in the computing power required to find the best solution. Sorting out where to put dinner guests is unlikely to be a valuable application of quantum computing, but it is an example of the challenge presented by, say, traffic routing options across a city. Even with powerful supercomputers, our ability to model complex situations currently requires computations that take weeks, months, or years. Quantum computing has the potential to change this, allowing us to solve and understand far more complex problems in science, manufacturing, logistics, finance, and security in minutes. This would reshape innovation and competition in many fields, allowing us to harness nature to transform the world. What is quantum computing? Quantum computing solves computational problems by utilizing the properties of quantum mechanics. Classical computing employs bits with values of 1 or 0, with answers derived through complex sequences based on manipulating these ones and zeros. A quantum bit is the quantum computing equivalent of a bit, qubit. A qubit can have a value of 1 or 0, but it can also have both values at the same time due to quantum behavior. This means that a qubit has the right value all of the time. The idea of tossing a coin is a useful analogy when thinking about qubits. When it is on the table, it has a value of either heads or tails, but when it is spinning, it can have both. Because a quantum computer's qubits can be in either a 0 or a 1 state simultaneously, it can try all possible combinations at once. However, because qubits contain both correct and incorrect numbers, the output is both correct and incorrect, so algorithms must be used to remove the incorrect answers and leave only the correct ones. Nonetheless, in quantum computing, the computational process to evaluate the options occurs only once, rather than multiple times sequentially. The power of a quantum computer can be calculated using 2n, where n is the number of qubits. A 50-qubit quantum computer, for example, could handle over 1,000 trillion numbers. A 300-qubit computer could process more numbers than the universe's atoms. Quantum computers are appealing for exponentially complex computational problems because they can address massive amounts of data concurrently. Applications. It is necessary to correct the perception of quantum computing as an evolutionary step forward from classical computing. Quantum computers are best suited to specific computational challenges, namely those with small inputs and outputs but infinite possibilities, because this directly maps onto the quantum mechanical behavior of a qubit. We will undoubtedly discover new and extraordinary applications for quantum computers that we cannot imagine today. However, for the time being, some potential applications include logistics, such as traffic flow management in smart cities and global shipment of goods. Weather forecasting, energy sources and production, and financial market forecasting are all examples of quantum chemistry encryption. During mission design, remote space exploration missions are optimized by modeling the brain and the world around us. What might a quantum computer do today? Are there any real-world applications of quantum computing technology, or a derivative thereof, that people are using right now? To put it another way, what exactly does quantum do, and who does it directly serve? Getting around, a GPS cannot function everywhere on the planet, especially underwater. A QC necessitates supercooling and suspending atoms in a state that makes them extremely sensitive. To capitalize on this, competing scientific teams are racing to develop a type of quantum accelerometer that could produce exact movement data. One promising effort in this direction comes from France's Laboratoire de Photonique Numérique ET Nanosciences, an effort to build a hybrid component that pairs a quantum accelerometer with a classical one, then subtracts the classical data from the quantum data using a high-pass filter. If realized, the result would be an extremely precise quantum compass, free of the bias and scale factor drifts commonly associated with gyroscopic components. Seismology, that same extreme sensitivity could be used to detect the presence of oil and gas deposits, as well as potential seismic activity, in areas that conventional sensors have previously been unable to explore. According to Quantic, the University of Glasgow's Quantum Imaging Technology Hub, Quantic demonstrated in July 2017, in collaboration with commercial photonics tools provider M², how a quantum gravimeter detects the presence of deeply hidden objects by measuring disturbances in the gravitational field. The team believes that if such a device becomes not only practical but also portable, it could be invaluable in an early warning system for predicting seismic events and tsunamis. Pharmaceutics, scientists at the forefront of research into diseases such as Alzheimer's and multiple sclerosis have been using software that models the behavior of artificial antibodies at the molecular level. In June 2017, neuroscience firm Biogen announced a collaboration with IT consultancy Accenture and QC research firm 1Qubit to develop a new molecular simulation model that can be executed on both classical and present and future quantum platforms. They hope to develop treatments for all types of dementia by modeling the natural neurodegenerative processes of the human brain. One method developed by 1Qubit's researchers entails converting traditional molecular diagrams into graphs full of dots, lines, and curves that, while appearing more complicated on the surface, map more directly to a quantum model of vectors and relationships. What could quantum computing accomplish in the future? Now for the more contentious question, suppose someone devised a mechanism that successfully overcomes the constraints imposed by quantum physics, yielding an entire quantum computer capable of performing all of the tasks currently reserved for theory and simulation. What do experts in this field believe a quantum computer should be able to do, assuming that every phenomenon theorized by physicists and observed and verified by scientists is ultimately exploitable? Physics, this one should be self-evident. It is the very reason for the concept's existence. Professor Richard Feynman, the father of quantum electrodynamics, QED, suggested in a 1981 speech at Caltech that the only way to build a successful simulation of the physical world at the quantum level would be with a machine that obeyed the laws of quantum mechanics. During that speech, Professor Feynman explained, and the rest of the world realized, that a computer could not simply generate a probability table and roll the dice. Furthermore, it would take a mechanism that behaved in the same way as the behavior it was supposed to simulate to produce results that physicists themselves would not produce. Machine learning, if and when quantum computers become stable enough to support thousands of qubits, machine learning algorithms are ready and waiting, having been thoroughly tested on paper and in simulators. Proponents' basic theory is that quantum systems may be designed to learn patterns of states in massive, concurrent waves rather than successive, sequential scans. If you read the previous paragraph, you already know what the problem is. Paper is a traditional system, just like electronic computers. As vectors in a wildly configurational space, conventional mathematics can circumscribe a set of likely quantum outcomes. However, as Richard Feynman stated from the start, it cannot simulate how those outcomes can be achieved. The first signs of widespread skepticism among experts that quantum machine learning is even possible were gently seeded into a report from MIT in October 2018 on a panel convened with IBM, where experts admitted that even after quantum computers become a reality, it may take several years before enough stable qubits are available to make quantum machine learning feasible. And there you have it, a glimpse into the fascinating world of quantum computing. The possibilities are endless, and we're just scratching the surface of what this technology can do. We hope you've enjoyed this exploration and learned something new. If you want to learn more about quantum computing and stay up to date with the latest breakthroughs, be sure to hit the subscribe button and turn on notifications. Thanks for watching, and we'll see you in the next video.